These are the answers to the AP Chemistry packet on topics 8.6 to 8.11. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now let's take a look at our first multiple choice question. In question 1, we are given the following information. It says, carboxylic acids are one common class of weak acid. The structural formula of lactic acid, HC3H5O3, is shown above and is an example of a carboxylic acid. Lactic acid undergoes an acid-base reaction with hydroxide ions according to the equation shown below. Which of the following correctly identifies the hydrogen atom in the lactic acid molecule that most readily participates in the reaction with the hydroxide ion and provides the correct justification? So you can see 4 answer choices, and in choices A and B, this particular hydrogen atom, which is directly bonded to oxygen in the center of the molecule, is circled, and in choices C and D, this particular hydrogen atom, which is located on the right side of this structural formula, also directly bonded to an oxygen atom, has been circled. So I think a good strategy for answering question 1 is to narrow down our answer choices. Is the correct answer to question 1 choices A or B? Or is the correct answer to question 1 choices C or D? Now, this particular question falls under topic 8.6, molecular structure of acids and bases. And one of the essential knowledge statements that you can see highlighted on this slide is that carboxylic acids are one common class of weak acid. And in my video that includes topic 8.6, I had mentioned carboxylic acids, and I had given a few examples of carboxylic acids. So what it says on this slide comes from that video for topic 8.6. I said, the acidic behavior of a carboxylic acid, which has the general formula RCO2H, where the letter R is an abbreviation for the rest of the molecule, and that often includes carbon atoms, hydrogen atoms, and sometimes even oxygen atoms. That general formula for a carboxylic acid, the acidic behavior of that acid, is supported by the fact that its conjugate base, which is known as the carboxylate ion, with the formula RCO2-, that conjugate base is stabilized by resonance. So let's remember resonance when we're considering the 4 choices in question 1. So what does resonance do to stabilize the conjugate base? Well, it delocalizes the negative charge over 2 different oxygen atoms in the structure. It's more stable if that negative charge can be delocalized over 2 different oxygen atoms than if that negative charge were localized on a single oxygen atom. That would be less stable. So delocalizing the negative charge over 2 different oxygen atoms helps to make it more stable. Now, also in that video that includes topic 8.6, I had given a few examples of carboxylic acids, and you can see them on this slide. So with propanoic acid and with salicylic acid, students had to circle the hydrogen atom that would be lost as an H+ ion when a carboxylic acid molecule reacts as a proton donor. And notice that the hydrogen atom is directly attached to this set of atoms that includes a carbon single bond and a carbon double bond. And that's where the resonance forms that I had shown you on the previous slide would be formed. So that carbon double bond next to a carbon single bond for CO double and CO single, that's where the resonance happens. Now, let's go ahead and consider the correct answer to question 1 in this packet. So it's definitely choices C or D because of the location of that hydrogen atom right next to that C double bond O, single bond O part of the molecule. If we had chosen choices A or B, when that hydrogen atom that's circled in choices A and B, when that hydrogen atom is removed as H+, then that oxygen would carry that negative charge, but there's no resonance structures possible. And so it would be better to delocalize the negative charge rather than to localize the negative charge on a single oxygen atom. So the correct answer to question 1, talking about resonance, is choice D, that the lactate ion C3H5O2- is made more stable by the delocalization of the negative charge on 2 different oxygen atoms through resonance. So the correct answer to question 1 is choice D. Now let's take a look at question 2. Question 2 says the following. The Lewis electron dot diagrams of the HOCl molecule and the HOI molecule are shown above. Which of the following identifies the substance that represents the stronger acid and correctly identifies a factor that contributes to its being the stronger acid? So if we look at these 4 answer choices, we can see that 2 of them, choices A and C, talk about London dispersion forces, and then the other 2 choices, B and D, talk about electronegativity and stabilizing the conjugate base. Now, just like question 1, this question falls under topic 8.6, molecular structure of acids and bases, and you can see that final essential knowledge statement that's highlighted on this slide says that electronegative elements tend to stabilize the conjugate base relative to the conjugate acid, and so increase acid strength. Let's talk more about electronegativity as it relates to these types of molecules. So in my video that includes topic 8.6, I had mentioned that there is a substance with the formula HOX, and that formula HOX represents a weak acid in which the X atom would be something such as chlorine, bromine, or iodine. And I said, as the electronegativity of the X atom increases, the strength of the acid also increases. And there are 2 reasons why this occurs. 1, as the electronegativity of the X atom increases, electron density is drawn away from the HO bond. This causes the HO bond to become weaker and more polar, favoring the breaking of the HO bond in the acid molecule, so that the molecule would lose H+ as a proton donor. And then the other reason is also related to electronegativity. As the electronegativity of the X atom increases, this helps to stabilize the conjugate base by pulling electron density away from the oxygen atom that carries the negative charge. And so as the conjugate base becomes more stable, the strength of the acid increases. So the correct answer to question 2 is going to be related to how electronegativity of that atom helps to stabilize the conjugate base. But now we have to consider which atom, chlorine or iodine, is more electronegative. Now on this slide, which comes from my video in Unit 1, this is for periodic trends, I had mentioned that as you move from top to bottom, the general trend in electronegativity is that electronegativity values tend to decrease from top to bottom as you move down a vertical column or a group on the periodic table. And you can see the halogens, fluorine, chlorine, bromine, and iodine, are highlighted there on that section of the periodic table. And fluorine is the most electronegative element on the periodic table. So looking at that trend, you can see that chlorine is more electronegative than iodine. So now we can answer question 2. The correct answer to question 2 is choice B, that the stronger acid is HOCl, And the factor that contributes to its being the stronger acid is that the chlorine atom is more electronegative than the iodine atom, and this helps to stabilize the conjugate base. So the correct answer to question 2 is choice B. Now let's take a look at question 3. In question 3, we see a table which has the title Properties of Bromothymol Blue. And question 3 says the following. Information about the properties of the indicator bromothymol blue is listed in the table above. A student uses bromothymol blue to test a solution in a beaker containing a mixture of hypochlorous acid, HOCl, which is a weak acid that has a pKa value of 7.54, and this mixture also contains sodium hypochlorite, or NaOCl. So it's a mixture of a weak acid and its conjugate base. Now, the color of the solution turns yellow after a few drops of bromothymol blue are added to the beaker. And the question says, based on the results of this experiment, which of the following is true about the pH of the solution in the beaker and the relative concentrations of the HOCl, or the hypochlorous acid, and the OCl minus, or the hypochlorite ion? Let's start with the pH of the solution first. So the low pH color of this indicator, and the pH range is between 6 and 7.6. The low pH color is yellow, and the high pH color is blue. But the experimental data tells us that the color of the solution turns yellow, which means that the pH range of the color change goes from 6 to 7.6. Therefore, a yellow color would indicate that the pH of the solution is less than 6. So we can eliminate choices C and D. The correct answer is either choice A or B. The pH of the solution for the low pH color, yellow, would be less than 6. Now, how do we decide the relative concentrations of HOCl and OCl minus? Well, this question falls under topic 8.7, pH and pKa. And I'll highlight that first essential knowledge statement. The protonation state of an acid or base, that is, the relative concentration of the weak acid, HA, and its conjugate base, A minus, can be predicted by comparing the pH of a solution to the pKa of the acid in that solution. And so here are two possibilities. We're not going to consider pH equal to pKa, but rather less than or greater than. So if the solution has a pH that is less than the pKa, then the acid form, or HA, would have a higher concentration. On the other hand, if the solution has a pH that is greater than the pKa, then the base form, or the A minus ion, would have a higher concentration. Now back to this particular question. So the pKa of hypochlorous acid is 7.54, and we have already determined that the pH of this solution, based on the fact that the color of bromothymol blue turned yellow, must be less than 6. So how does a pH of 6 compare with a pKa value of 7.54? Since the pH of this solution is less than the pKa for hypochlorous acid, then that means that the acid, HOCl, must have a higher concentration than its conjugate base, OCl minus. So based on that information, the correct answer to question 3 is choice A. We know the pH of the solution is less than 6 because of what happened to bromothymol blue, and we know that since pH is less than pKa, then the acid, HOCl, must have the higher concentration. So correct answer to question 3 is choice A. Now let's take a look at question 4. In question 4, we can see a graph that represents a titration curve from a titration experiment, and we are given the following information. It says a sample of NH3, which is ammonia, is titrated with HCl, hydrochloric acid. The pH of the solution is measured with a pH meter and graphed as a function of the volume of HCl added, as shown in the graph at right. A student carries out the same titration but wants to use an indicator instead of a pH meter. Information about two different indicators is listed in the table below. So we have two indicators. We have methyl red, which has a pKa value of 5.0, and we also have phenolphthalein, which has a pKa value of 9.4. So now the question asks, which of the following identifies the best indicator to use for the titration and provides the correct justification? Now, this question also falls under topic 8.7, pH and pKa, and take a look at this final essential knowledge statement that I've highlighted on this slide. It says, to ensure accurate results in a titration experiment, acid-base indicators should be selected that have a pKa value that is close to the pH of the solution at the equivalence point. Let's go ahead and take a look at the titration curve. And where is the location of the equivalence point? Well, that's going to be where that rapid change in pH occurs, which on the x-axis would be after 30 milliliters of hydrochloric acid is added. Now, to estimate the pH at the equivalence point, it's normally in the middle of that rapid change in pH. So I'm going to estimate that the pH of the solution at the equivalence point is approximately somewhere between pH 5 and pH 6. And to choose an indicator whose pKa value is close to the pH of the solution at the equivalence point, that tells us that methyl red would be the better choice. So the pH of the solution at the equivalence point is somewhere between 5 and 6, and the pKa of methyl red is 5.0. Phenolphthalein would not be a good choice because that indicator would change color in the vicinity of pH 9, and that would not indicate the pH of the solution at the equivalence point. So we know that our answer to question 4 is methyl red, which means the answer is either A or B, but let's focus on the equivalence point, not the half equivalence point, but rather the equivalence point. So the correct answer to question 4 is choice B. Methyl red should be chosen because the pKa value of methyl red is close to the pH of the solution at the equivalence point. Now let's take a look at question 5. In question 5, it says the following. A solution is prepared by combining equal volumes of 1.0 molar HF, which is hydrofluoric acid, and 1.0 molar NaF, which is sodium fluoride, in a beaker. And the question asks, which of the following correctly predicts how the pH will change if a small amount of HCl, hydrochloric acid, or NaOH, sodium hydroxide, is added to the beaker, and provides the correct equation for the reaction that accounts for the relatively small change in pH. So this question, question 5, is about buffers. We have a buffer solution that contains a weak acid, HF, and its conjugate base, F-. So how will a buffer respond if either a small amount of a strong acid, such as HCl, is added to the buffer, or if a small amount of a strong base, such as sodium hydroxide, is added to the buffer? This question falls under topic 8.8, properties of buffers, and the essential knowledge statement says, a buffer solution contains a large concentration of both members in a conjugate acid-base pair. So in this particular example, that would be HF and F-. Now the conjugate acid, so HF, will react with the added base, and then the conjugate base, F-, will react with added acid. And these reactions are responsible for the ability of a buffer to stabilize pH. Now, in my video that included topic 8.8, I had mentioned the following details about buffer solutions. So on this slide, what I'm talking about is what happens if a small amount of a strong acid is added to a buffer. So the A minus, the conjugate base, would react with the H plus ions or the hydronium ions to produce the weak acid HA and water. Now, that ratio of the concentrations of A minus and HA will change, but only slightly. And when you add a small amount of a strong acid to a buffer, then the pH will decrease, but only slightly. On the other hand, if a small amount of a strong base is added to a buffer solution, then the weak acid, HA, would react with those hydroxide ions from the strong base, and then the products would be A minus, the conjugate base, and water. Again, that ratio of the concentration of A minus and HA would change, but only slightly. And if a small amount of a strong base is added to a buffer, the pH will increase, but only slightly. Now, the specific details in question 5 involve HF, which is the weak acid in this buffer, and F minus, which is the weak base in this buffer. So again, this is a conjugate acid-base pair. So if a small amount of hydrochloric acid or any strong acid is added to this buffer, then the F minus ions would react with either H plus ions or hydronium ions to produce the weak acid HF and water. And the pH would decrease, but only slightly. On the other hand, if the small amount of sodium hydroxide or any strong base is added to this buffer, now the HF molecules would react with the hydroxide ions from the strong base, and the products would be the F minus ion and water. And the pH would increase, but only slightly. Now let's examine the 4 choices listed in question 5 so we can possibly narrow down our choices and eliminate some wrong answers. In choices A and B, we can see that that would be a strong acid, hydrochloric acid. We know that the pH will decrease slightly. So we can eliminate choice B, which says that when HCl is added, the pH will increase. That's not true. The pH would decrease when a strong acid is added. So I can eliminate choice B. Moving on to choices C and D, we have sodium hydroxide, a strong base. We know the pH would increase slightly, but choice C says that sodium hydroxide would cause the pH to decrease. That's not true. We can eliminate choice C. So possibilities for answers in question 5 are either A or D based on the direction of how the pH will change. Now let's look at those equations for the reaction that would account for the relatively small change in pH. So in choice A, it says hydronium, H3O plus F minus to produce HF and water. That's exactly what would happen. So choice A looks like the correct choice, and if you examine choice D, it indicates that the hydroxide ions are reacting with F minus. That's incorrect. The hydroxide ions would react with the HF molecules, not the F minus ions. So we can eliminate choice D. The correct answer to question 5 is choice A. If a strong acid such as HCl is added to this buffer, the pH will decrease slightly, and it's because some of the F minus is consumed by the hydronium ions, producing additional molecules of HF, but that ratio of F minus to HF would only change slightly. And the pH will decrease, but only slightly. All right, so question 5 is choice A. Now let's take a look at question 6. Question 6 says the following. Ethylamine, which has the chemical formula C2H5NH2, reacts with water according to the equation shown above. So if we look at the details of this chemical equation, we can see that ethylamine is behaving as a weak base. It's a proton acceptor, so it accepts the H plus ion from water, to produce hydroxide ions, OH-, and also it forms its conjugate acid, which is C2H5NH3+, that's called the ethylammonium ion. Now, a buffer solution is prepared that contains equimolar amounts of this conjugate base acid pair. So ethylamine is the weak base in this buffer, and then the ethylammonium ion is its conjugate acid in this buffer. So there's the buffer, and when a small amount of 12 molar HNO3, which is nitric acid, that's a strong acid, is added to this buffer solution, the pH of the solution changes from 10.75 to 10.73. So a good buffer will have a small change in pH, and that's what's happening here. The strong acid is added to the buffer, and the pH decreases, but only slightly. Now here comes the question. Which of the following equations represents the reaction that accounts for the fact that the pH does not change significantly when a small amount of nitric acid is added? Now on this next slide, I'll just show you, here's the structure of the ethylamine molecule. And there's a lone pair of electrons on that nitrogen atom, and that's where the ethylamine is acting as a proton acceptor. So it accepts the proton from the water molecule. That will form the hydroxide ion, but then it also produces its conjugate acid, which is the ethylammonium ion. So in this buffer system, ethylamine is the weak base, and the ethylammonium ion is the weak acid. So ethylamine, C2H5NH2, is the weak base, and the ethylammonium ion, C2H5NH3+, is the conjugate acid. Now on the equation sheet, you can see I've highlighted the Kb expression. So what exactly does that capital B represent? Well, capital B is the generic formula for a molecule of a weak base. And if it reacts with water, then you get hydroxide ions, so OH-, but you also get the conjugate acid ion represented as Hb+. So B would represent the generic formula for a weak base molecule, and Hb+ represents the generic formula for the weak acid ion, the conjugate acid. Now we have our buffer system, and a small amount of nitric acid is added. So if any strong acid is added to this buffer, it will be the weak base molecule, I'll represent this as capital B, would react with either the hydronium ions, H3O+, to produce the conjugate acid ion, Hb+, and water, or you could simplify this reaction between the weak base B, you could just react it with H+ ions. And if I choose H+ ions, then the only product would be Hb+. Now let's substitute ethylamine, C2H5NH2, for the generic formula B for a weak base. So here's the ethylamine reacting as a proton acceptor with either the hydronium ion to produce the weak acid, the ethylammonium ion, and water, or you could simplify this reaction by substituting hydronium with H+. So the ethylamine would react with H+ ions to produce its conjugate acid, the ethylammonium ion. So why would this buffer system result in a slight decrease in pH? What happens is the ratio of ethylamine to ethylammonium will change, but only slightly. So molecules of ethylamine are converted into the ion, the ethylammonium ion. The ratio in the buffer components changes, but only slightly, and therefore the pH will decrease, but only slightly. Now let's look at the 4 answer choices for question 6. Hopefully you can see, after me sort of explaining what was going on in terms of ethylamine being converted into the ethylammonium ion, that choice A is the correct answer. Choice B is incorrect because it shows a positive ethylammonium ion reacting with H+ ions. So that's not possible for the ethylammonium ion to be a proton acceptor. So choice B is incorrect. And the reactions in choices C and D are not specifically referring to this ratio of the weak base and its conjugate acid. So correct answer to question 6 is choice A. Now, as we move on to question 7, we're going to see a similar type of question in which a buffer solution is prepared, but in question 7, a small amount of a strong base will be added to the buffer. Let's take a look at question 7. Question 7 says the following. Methanoic acid, which has the chemical formula HCOOH, that's a weak acid. By the way, methanoic acid is the simplest formula for a carboxylic acid. I talked about carboxylic acids back in question 1 in this packet. So methanoic acid, the weak acid, reacts with water according to the equation shown above. So in this equation, we can see that methanoic acid is a proton donor. So it donates H plus to water, forming the hydronium ion H3O+, along with its conjugate base, which is the methanoate ion, and that has the formula HCOO-. Now we have a buffer solution with a conjugate acid-base pair. So a buffer solution is prepared that contains equimolar amounts of methanoic acid, the weak acid, and its conjugate base, the methanoate ion. Now, when a small amount of 12 molar KOH, or potassium hydroxide, that's a strong base, is added to this buffer solution, the pH of the solution changes from 3.74 to 3.76. So the pH increases, but only slightly. And here comes the question. Which of the following equations represents the reaction that accounts for the fact that the pH does not change significantly when this strong base, potassium hydroxide, is added? So in our buffer system, we have a weak acid, that's methanoic acid, along with its conjugate base, the methanoate ion. Now on the equation sheet, this time instead of highlighting the Kb expression, I'm highlighting the Ka expression. So what does HA represent? Well, HA is the generic formula for a weak acid. If it reacts with water as a proton donor, it forms the hydronium ion H3O+, along with its conjugate base, A-. So HA is the generic formula for a weak acid molecule, and then A- is the generic formula for a weak base ion, the conjugate base. So here's our buffer system. We have the weak acid, methanoic acid, and then we have the weak base, the conjugate base, the methanoate ion. Now, if a small amount of potassium hydroxide or any strong base is added to this buffer, it will be the weak acid reacting with the hydroxide ions. So here's the generic formula HA reacting with hydroxide ions from the strong base to produce the conjugate base, A-, and water. Now let's substitute the formula for methanoic acid for HA. So here's the methanoic acid, again, reacting with the hydroxide ions from the strong base. It will produce its conjugate base, the methanoate ion, and water. So why does the pH increase but only slightly? It's because this ratio of buffer components, as in the ratio of the methanoic acid and the methanoate ion, it will change. That ratio of ions to acid molecules, it will change, but only slightly. And that will keep the pH changing only slightly in this buffer. So let's look at the 4 choices for question 7. Hopefully you can see why choice B is the correct answer. Choice A is incorrect because it shows the methanoate ion, which is a weak base, reacting with the hydroxide ion from the strong base. So that equation is incorrect. The methanoate ion would be a proton acceptor, not a proton donor in choice A. That's incorrect. Choice B shows the methanoic acid being converted into ions of its conjugate base, the methanoate ion, and the buffer components are changing but only slightly. Choices C and D are incorrect because they don't feature how the components of this buffer system would be changing. So the correct answer to question 7 is choice B. Again, questions 6 and 7 were very similar to each other, both involving net ionic equations for how a buffer will respond when either a strong acid or a strong base is added to the buffer. Now let's take a look at question 8. In question 8, we can see two different particulate diagrams, and in question 8, we're given the following information. This also will involve a buffer solution. It says, a student measures the pH of a solution in a beaker that contains equimolar amounts of HC2H3O2, that's acetic acid, that's a weak acid, and NaC2H3O2, that is sodium acetate, that's the conjugate base of acetic acid, and records the pH as 4.74. So that is a buffer solution, equimolar amounts of a weak acid and its conjugate base. Then the student adds a small amount of an unknown solution to the beaker and stirs the mixture thoroughly. Now the identity of the unknown solution is either HCl, hydrochloric acid, that's a strong acid, or NaOH, sodium hydroxide, that's a strong base. Now the particulate diagrams shown below represent the relative amounts of acetic acid molecules and acetate ions, again that's a conjugate acid-base pair, in a sample of the solution in the beaker before and after the unknown solution is added. So we need to use the information in these two particulate diagrams to determine what was the identity of the unknown solution that was added. Was it a strong acid or was it a strong base? And it says, note that water molecules and ions such as sodium ions or chloride ions are omitted. Now the question is, which of the following correctly identifies the unknown solution that is added to the beaker, so either hydrochloric acid or sodium hydroxide, and describes the pH of the mixture at the end of the experiment. So the initial pH before that unknown solution is added was 4.74, and at the end of the experiment is the pH less than or greater than 4.74. Well, the first thing I'm going to do is count the particles in that particulate diagram on the left. 1, 2, 3, 4, 5 molecules of the weak acid, acetic acid. Now, as far as the acetate ion, the conjugate base, I see 1, 2, 3, 4, 5. So we have an equal amount of moles of the weak acid and the conjugate base. So that pH of 4.74, that is also equal to the pKa for acetic acid. pH equals pKa. Now, a small amount of an unknown solution is added to the beaker. Let's see how the components in that particulate diagram on the right are different than the diagram on the left. So I'll start by counting the acetic acid molecules. 1, 2, 3, 4. So I lost one of those acetic acid molecules. And if I count the acetate ions, I get 1, 2, 3, 4, 5, 6. So now I can determine what happened as a result of that small amount of unknown solution that was added to the beaker. Some of the acetic acid was transformed or converted into the acetate ion. So what type of substance, a strong acid or a strong base, would convert acetic acid into acetate? Well, hopefully you can see that H+ would not be possible, or hydronium would not be possible, but rather the hydroxide ion could remove the proton from the acetic acid and produce water along with the acetate ion, the conjugate base of acetic acid. So now we have determined that it was hydroxide ions that did this particular change to the particulate diagram, so therefore the unknown solution that is added to the beaker must contain hydroxide ions. It must be a strong base. Let's go ahead and eliminate choices A and B, which say hydrochloric acid. It must be choices C or D, sodium hydroxide, the strong base. Now, when the pH is greater than the pKa, this is topic 8.7, then you have more A- than HA. So when the pH is greater than the pKa, you have more of the conjugate base A- than the weak acid HA. And that's exactly what happened in this experiment. We have more acetate than acetic acid. So we have more A- than HA. So the pH should be greater than the pKa. So correct answer to this question is choice D. All right, now let's go ahead and take a look at question 9. In question 9, it says the acid dissociation constants, which are the Ka values, of two different weak acids. One has the chemical formula HC3H5O3, and the other weak acid has the chemical formula CH3NH3+. So we have two different Ka values that are given in the table above. And the question asks, which of the following mixtures would produce a buffer solution with a pH of approximately 3? Now, this question definitely has to do with properties of buffers, but I'm going to show you on this slide topic 8.5, acid-base titrations. And the essential knowledge statement that's highlighted on this slide says the following. For titrations of weak acids and bases, it is useful to consider the point halfway to the equivalence point, that is the half equivalence point. At this point, there are equal concentrations of each species in the conjugate acid-base pair. So for example, if you have the same concentration of the weak acid HA as the conjugate base A-, then pH equals pKa at this point. So now these slides come from my video for topic 8.8, properties of buffers. And what I can show you here are a variety of combinations to produce a buffer at a particular pH. So the first one I will highlight is HClO2, which is chlorous acid. And if I have a pKa of 1.96, I would need to prepare a buffer with equimolar amounts of chlorous acid and its conjugate base, the ClO2- ion. Then pH would equal pKa, and that would be 1.96. If instead I had an equimolar mixture of hydrofluoric acid and the fluoride ion, then pH would equal pKa, and that would be 3.17. And as you recall from a previous question in this packet, if I have an equimolar mixture of acetic acid and acetate, then pH equals pKa, and that would be 4.74. But how exactly do we prepare a buffer? Well, in my video for topic 8.8, properties of buffers, I had mentioned that there are 4 possible combinations that should result in the formation of a buffer solution with equimolar amounts of the weak acid and the conjugate base. Now, the one that I'm highlighting is the one involving a half titration, where you take a weak acid such as HA, and then you add a strong base, but not to get to the equivalence point. Instead, to get to the half equivalence point. By getting to the half equivalence point, that means that half of the HA molecules would be converted into A- ions of the conjugate base, and that would produce an equimolar mixture of HA and A-. And I mention that because in these 4 choices in question 9, we can see a weak acid, so either of those acids listed in the table above, combined with a strong base. And what we want is the half titration, or the half equivalence point. We do not want to go all the way to the equivalence point, because that would not be a good buffer solution. If we go all the way to the equivalence point, then we convert all of the weak acid into the conjugate base, but we only want to convert half of the weak acid to its conjugate base. All right, let's consider number of moles. In all 4 of these choices, we have 100 milliliters of a 0.10 molar solution of the weak acid. So 0.1 liters times 0.1 moles per liter would give me 0.01 moles of the weak acid. Now, looking at choices A and B, instead of 100 milliliters of a 0.1 molar solution, it's only 50 milliliters of a 0.1 molar solution of sodium hydroxide. That would give us the half equivalence point. So the combination of solutions in choices A and B would result in that half equivalence point. So what about choices C and D? Well, instead of using half of the amount of moles, we have 100 milliliters of a 0.1 molar solution of sodium hydroxide. And what that would do is get you all the way to the equivalence point. So the combination of solutions in choices C and D would not reach the halfway point in the titration. They would go all the way to the equivalence point. So in choices C and D, whatever that weak acid is, it would be completely converted into its conjugate base, and that would not produce a good buffer solution. So the correct answer to question 9 is either choices A or B. Now we're looking for a buffer solution that has a pH of approximately 3. So let's go ahead and take the pKa, as in the negative log of the Ka. So in choices A and B, since half of the weak acid would be converted into its conjugate base, we would get that perfect pH equals pKa situation that results at the half equivalence point of a titration. Okay, so what's the negative log of 8.3 times 10 to the negative 4? That pKa value is 3.1. If we take the negative log of 2.3 times 10 to the negative 11, that pKa value is 10.6. But we're looking for a buffer solution with a pH of approximately 3. So that makes A the best answer in question 9. Now, choice B would make a good buffer solution, but the pH of that buffer solution would be approximately 10.6. So correct answer to question 9 is choice A. And again, that was a half titration resulting in the half equivalence point. pH equals pKa equals 3.1. All right, now let's take a look at question 10. In question 10, it says a student attempts to prepare a buffer solution with a pH of 7.5 by adding HOCl, which is hypochlorous acid, that's a weak acid, and NaOCl, that's sodium hypochlorite. The hypochlorite ion is the conjugate base of the weak acid. Now the pKa of this weak acid is 7.54. So they're adding HOCl, the weak acid, and NaOCl, the conjugate base, to distilled water. Now the desired pH is 7.5, but instead of the desired pH, the measured pH of the buffer solution is not 7.5, but rather 7.0. So here comes the question. Which of the following is the most likely reason that the pH is too low? This is about pH versus pKa. So topic 8.7, pH and pKa. When the solution has a pH that is less than the pKa, then the acid form, as in HA, would have a higher concentration than the base form, A-. So pH less than pKa, there should be more HA than A-. But specifically, that would mean more HOCl than OCl-. So pH is less than the pKa because 7 is less than 7.5. There should be more of the hypochlorous acid, HOCl, than there is the conjugate base, the OCl- or the hypochlorite ion. Well, hopefully you can see that the correct answer would be A. If there's a higher concentration of HOCl than OCl-, then too much HOCl was used. Choice B, if that were true, if too much of the OCl- was used, then the pH would be too high, not too low. And the reason why choice C is incorrect is because diluting the components of a buffer does not change the pH. Diluting a buffer with water does not affect the mole ratio and does not change the pH. And then choice D is also incorrect because there's no requirement that a few drops of a strong base are added. To prepare this buffer, we can simply mix the weak acid and its conjugate base, but a few drops of a strong base are not required to prepare this buffer. So pH is too low, too much of the weak acid, HOCl. Correct answer to question 10 is choice A. Now let's take a look at question 11. Question 11 says the following. The Ka value of hydrofluoric acid, HF, is equal to 6.8 times 10 to the negative 4. And the question asks, which of the following mixtures would produce a solution with a pH that is closest to 3.5? Now, looking at these four answer choices, we have 50 milliliters of a HF solution being combined with 50 milliliters of either sodium fluoride or sodium hydroxide. So question 11 falls under topic 8.9, the Henderson-Hasselbalch equation. So you can see that the equation is listed here on this slide, and what I'm going to do is replace the HA and the A minus with the specific formula hydrofluoric acid, HF, and then its conjugate base would be the fluoride ion, F minus. Now what I'm going to do is take the negative log of the Ka so I can calculate the pKa. So the negative log of 6.8 times 10 to the negative 4, that works out to be 3.17. But it says, which of the following mixtures would produce a solution with a pH that is closest to 3.5? Not 3.17, 3.5. And since the pH that we are looking for is greater than the pKa, this tells me that we need more of the conjugate base, F minus, than the weak acid HF. So as I examine the four choices listed in question 11, I'm looking for a scenario in which the concentration of F minus is greater than the concentration of HF. So I'll start with choice A. I see 50 milliliters of a 1.0 molar solution of HF combined with 50 milliliters of a 1.0 molar solution of sodium fluoride. Well, that would result in equal concentrations of HF and F minus. The pH would equal the pKa of 3.17, so I can eliminate choice A. Now moving on to choice B. 50 milliliters of 1.0 molar HF, and now 50 milliliters of 2.0 molar sodium fluoride. That would produce a solution in which the concentration of fluoride is greater than the concentration of HF. So that choice, B, has potential as being the correct answer. I'll move on to choice C. Now we start with 50 milliliters of 1.0 molar HF, but this is not combining it with sodium fluoride. This is combining it with sodium hydroxide, so we're doing a titration in choice C. Are we stopping at the half equivalence point? No, we're actually going all the way to the equivalence point. If I combine equimolar amounts of HF and the hydroxide from sodium hydroxide, then this weak acid would be completely converted into its conjugate base, F minus. So this would not be a good buffer solution. In fact, it would turn it into a solution of fluoride, and because fluoride acts as a weak base, that pH would be greater than 7, so not 3.5. Now, finally, in choice D, we do have a mixture of HF and NaF. So 50 milliliters of 2 molar HF and 50 milliliters of 1 molar sodium fluoride. But unfortunately, it's the wrong direction for what I'm looking for. The concentration of HF in choice D is actually greater than the concentration of F minus. Choice D would give me a pH that is less than 3.17. I'm pretty confident that the correct answer to question 11 is choice B, but I still haven't used the Henderson-Hasselbalch equation to confirm what this pH is. So I'm going to go ahead and plug in 3.17 for the pKa, and notice that in choice B, the ratio of fluoride to HF is a 2-to-1 ratio. That means that that ratio would be 2/1, and the log of 2 is equal to 0.30. So 3.17, the pKa, plus the log of 2, 0.30, gives me a pH of 3.47, and that is pretty close to 3.5, which is why choice B is the correct answer to question 11. All right, now let's take a look at question 12. Question 12 says the following. The Ka value of acetic acid which has the formula HC2H3O2, that's a weak acid, is equal to 1.8 times 10 to the negative 5. A buffer solution is prepared by mixing 500 milliliters of 2.0 molar acetic acid and 500 milliliters of 1.0 molar sodium acetate, which has the formula NaC2H3O2. So the weak acid is acetic acid, and then its conjugate base, acetate, is being combined together. But notice that the amount of moles of the weak acid and the conjugate base are not exactly the same. Now the question asks, the pH of this buffer solution is closest to, and we have 4 answer choices. This will be a Henderson-Hasselbalch calculation. So there's the generic form of the equation, but I'd like to substitute for HA and A minus with the actual chemical formulas. So the acetic acid would go on the bottom, and then the acetate would go on the top in that ratio. Now I'm going to calculate the pKa by taking the negative log of the Ka. So the negative log of 1.8 times 10 to the negative 5 is equal to 4.74. Now, is the correct answer to question 12 choice B? No, because we don't have an equimolar mixture of the weak acid and the conjugate base. In fact, if we look at the details, we have a higher concentration of the acetic acid, 2 molar, and we have a lower concentration of the sodium acetate, 1 molar. So we have the same volume, but we don't have the same concentration. So there is a 2-to-1 ratio of acetic acid to acetate. Now, in our equation, that would mean that we'll be putting 1 on the top and 2 on the bottom in that ratio. So the 1 would correspond to the acetate, and the 2 would correspond to the acetic acid. So 4.74 is the pKa. What's the log of 1/2? Well, the log of 1/2 is negative 0.30. So 4.74 plus a negative 0.30 gives us the answer to question 12, which is a pH of 4.44. Now, just a final comment on this question. Because the concentration of the weak acid in this buffer is greater than the concentration of the conjugate base. In other words, the concentration of acetic acid is greater than the concentration of acetate. We have the following situation. pH should be less than pKa. So when the concentration of the weak acid is greater than the concentration of the conjugate base, pH is less than pKa, and 4.44 is definitely less than 4.74. All right, now let's move on to question 13. In question 13, we are given a table, and it says, 2 buffer solutions are prepared, and the concentrations of each buffer component are listed in the table above. And the question asks, which of the following correctly compares the pH and the buffer capacity of solutions 1 and 2? So question 13 falls under topic 8.10, buffer capacity. And the essential knowledge statement that's highlighted on this slide says the following. Increasing the concentration of the buffer components while keeping the ratio of these concentrations constant keeps the pH of the buffer the same, but increases the capacity of the buffer to neutralize added acid or base. In other words, a larger concentration of buffer components will lead to a larger buffer capacity. Now let's analyze solutions 1 and 2. As you can see, we have HNO2, which is a weak acid, and we have NO2 minus, its conjugate base. So for solution 1, the concentration of each of those components is equal, but it's 0.10 molar. With solution 2, the concentration of the buffer components is still equal, but now it's 1 molar, so a much higher concentration of buffer components. So the concentrations of buffer components in solution 2 are larger than that of solution 1. Therefore, we can conclude that solution 2 has a larger buffer capacity. Let's look at the 4 choices. larger buffer capacity for solution 2, larger buffer capacity for solution 2. We can eliminate choices A and C, which indicate that they have the same buffer capacity. They do not. Now, what about the pH? Well, here is the Henderson-Hasselbalch equation. pH equals pKa plus log of A minus over HA. So specifically, that would be the NO2 minus over the HNO2. But look at that ratio. The ratio of the NO2 minus ion to HNO2, it's 1:1. So pH equals pKa for both solution 1 and solution 2 because the ratio is 1. So these buffer solutions have the same pH. So the correct answer to question 13 is the following. Same pH, but larger buffer capacity for solution 2. So correct answer to question 13 is choice B. Now let's take a look at question 14. In question 14, we are given a table and it says 2 different buffer solutions, X and Y, are prepared by combining solutions of NH3, which is ammonia, a weak base, and NH4+, which is ammonium, the conjugate acid of ammonia. A student records the initial pH of each buffer solution and then adds 10 milliliters of 10 molar nitric acid, a strong acid, to 1 liter of each buffer solution. The student correctly measures the final pH of each solution. Data from the experiment are shown in the table above, and so here's the question. Which of the following correctly compares the buffer capacity of solutions X and Y and provides the correct justification? Now, unlike the previous question where we actually had the concentrations of the buffer components, in this table we do not. We don't have the concentrations of ammonia and ammonium. What we do have is the initial pH before the strong acid is added, and then the final pH after the strong acid is added. So on this slide, from my video for topic 8.8 talking about buffer properties, you can see a comparison of what happens to the pH when a small amount of a strong acid is added to a buffer solution versus what happens when that same amount of strong acid is added to pure water, which is not a buffer. So you can see that when 0.040 molar of the strong acid or the hydronium ion was added to that buffer solution, the pH decreased only a little bit, from 4.74 to 4.70. But then, as a comparison, if you add that same amount of hydronium ion to pure water, the pH decreased from 7 all the way down to 1.4. So the power of a buffer is to maintain a relatively constant pH when a small amount of either a strong acid or a strong base is added to the buffer. So a good buffer solution should keep the pH relatively constant after a small amount of strong acid or strong base is added to it. Now, looking at the information in this table, which buffer solution, X or Y, was able to keep the pH relatively constant? So for solution X, the initial pH is 9.3, and then after the strong acid is added, the final pH is 9.2. So that's pretty good. Now, for solution Y, initially the pH was 9.0, but then after the strong acid was added, the pH went all the way down to 2.2. That's not a good buffer. So here's our conclusion. Buffer X did a better job of keeping the pH relatively constant, so therefore we can assume that buffer X should have the higher buffer capacity. It was better at maintaining a relatively constant pH. Now, looking at our 4 answer choices, we're looking for solution X having a larger buffer capacity than solution Y. So the correct answer is either A or B. And with respect to the justification, it's not about the initial pH, it's about that relatively small change in pH. So the correct answer is choice B. Solution X has a larger buffer capacity than solution Y because the change in pH for solution X is much smaller than the change in pH for solution Y. All right, now let's take a look at question 15. Question 15 says the dissolution of magnesium hydroxide in water is represented by the equation above. The KSP of magnesium hydroxide is 5.6 times 10 to the negative 12. And the question asks, which of the following changes will increase the solubility of magnesium hydroxide in an aqueous solution? Now, this question falls under topic 8.11, pH and solubility. And the essential knowledge statement says that the solubility of a salt is pH sensitive when one of the constituent ions is a weak acid or base. These effects can be understood qualitatively using Le Chatelier's principle. So I'm going to start by analyzing these four answer choices from bottom to top. So starting with choice D. Choice D says adding magnesium nitrate to the solution. Well, adding magnesium nitrate would result in an increase in the concentration of magnesium ions. And if the concentration of magnesium ions increases, then QSP becomes greater than KSP. And if that happens, then the equilibrium for the dissolution of magnesium hydroxide would experience a net conversion from right to left, from products to reactants, but that would result in the solubility of magnesium hydroxide decreasing, not increasing. It would shift the equilibrium toward the formation of the solid, making it less soluble. So the correct answer is not choice D. Now, what about choice C, adding ammonia or NH3 to the solution? Well, ammonia is classified as a weak base. And if you are classified as a weak base, then you will produce hydroxide ions in solution. So the presence of a weak base will cause the value of the concentration of hydroxide ions to increase. And if that happens, if the concentration of hydroxide ions increases, then QSP becomes greater than KSP. Same situation as in choice D. There would be a net conversion from right to left, from products to reactants, again, decreasing the solubility of magnesium hydroxide. So we can eliminate choice C. Now we're down to pH. Remember, this is topic 8.11, pH and solubility. So is it decreasing the pH or increasing the pH? Increasing the pH will cause the value of the concentration of the hydroxide ion in the solution to increase, which means QSP becomes greater than KSP, and a net conversion from right to left, from products to reactants. Again, decreasing the solubility of magnesium hydroxide. So I'm basically telling you that the answer is A, but let's go ahead and take a look at why the correct answer is A. So decreasing the pH will result in an increase in either H plus ions or hydronium ions. And what did the hydronium or the H plus ions do to this equilibrium? Well, they will react with the hydroxide ions in the solution, and so it's going to do the opposite of choice B. Instead of increasing the concentration of hydroxide ions, it's going to be the opposite of that. So as the additional H plus ions from the acid react with the hydroxide ions in the magnesium hydroxide equilibrium, the value of the concentration of the hydroxide ion actually decreases. Now, Q becomes less than K. So QSP becomes less than KSP. There should be a net conversion from left to right, from reactants to products, and yes, this would actually cause the solubility of magnesium hydroxide to increase in the presence of an acid. So decreasing the pH would increase the solubility of magnesium hydroxide. All right, well, that is the answer to question 15, which is choice A. Now we're going to see another question involving pH and solubility. This is question 16. Question 16 says the following. The dissolution of calcium fluoride in water is represented by the equation above. The KSP of calcium fluoride is 3.9 times 10 to the negative 11. The molar solubility of calcium fluoride increases when it is dissolved in 0.50 molar HNO3, which is nitric acid, that's a strong acid, instead of neutral distilled water. So the molar solubility of calcium fluoride increases in the presence of an acid as compared to neutral distilled water. So here's the question. Which of the following represents the balanced net ionic equation for the process that occurs between species in solution that contributes to the increased solubility of calcium fluoride in nitric acid? So we are already told that the molar solubility of calcium fluoride is affected by the presence of the strong acid. It increases the solubility. And if the solubility of calcium fluoride increases, then the equilibrium for the dissolution of calcium fluoride would experience a net conversion from left to right, from reactants to products. We know that nitric acid is a strong acid and represents a source of H+ or hydronium ions. What we need to consider is which of these four reactions would best explain this shift in the equilibrium from left to right, making it even more soluble in the presence of an acid. Now, I'm going to start with choice D. And the reason why is because of something we had learned back in Unit 4. These are the soluble ions, the soluble snap ions, sodium, nitrate, ammonium, and potassium. So take a look at choice D. It shows that calcium would combine with nitrate ions to produce solid calcium nitrate. But that's not consistent with the fact that nitrate is one of those soluble snap ions. So calcium nitrate would not be a precipitate. Calcium nitrate should be soluble in water, so I can eliminate choice D. That equation to produce a precipitate of calcium nitrate is incorrect. Now, moving on to choice C. What it shows is basically the reverse of the dissolution of calcium fluoride. So the equation in choice C actually shows the precipitation of solid calcium fluoride. And this equation does not explain why the solubility of calcium fluoride actually increases when it is dissolved in a strong acid solution. So now we're down to either choices A or B. Now HF is actually a weak acid. HNO3 is a strong acid. Well, if HF is a weak acid, then the F- ion is a weak base. So take a look at choice A. The fluoride ion, which behaves as a weak base, would react with the hydronium ions from the strong acid. And as a result of that reaction between fluoride ions and hydronium ions, it causes the value of the concentration of the fluoride ion to decrease. Now, what does that do in terms of the Q versus K? Well, decreasing the concentration of fluoride would result in a situation where now QSP becomes less than KSP. And now there will be that net conversion from left to right, from reactants to products, as a result of that decrease in the fluoride ion concentration. And that would explain why the solubility of calcium fluoride actually increases in the presence of a strong acid. So choice A is the correct answer to question 16. And so question 16 is the last question in this packet, so we have come to the end of this video. I hope that you found all of these answers and explanations helpful. Thanks for watching.